All right, everybody. Everyone hear me okay? Awesome. That's good to hear. Kanye and I were meeting earlier and having some problems with the microphones. This is good news. Um, yeah, a couple announcements, logistics type things. Obviously, for those that usually attend in person, we're online indefinitely until I hear back about the room. I guess Sakanya went in yesterday and the TVs were still not fixed. She reached out to Chantel yesterday. And so should have a couple tickets to get that room fixed by now. So hopefully it's better pretty quick, so we can be back in person. Otherwise, we have homework due on Friday. It's homework 5. I'll be holding additional office hours tomorrow after class to help you all with that. I think Sakanya is holding some more later this week as well. It is actually, after kind of walking through with Sakanya earlier today, quite a bit shorter. The answers are pretty short and succinct, so shouldn't be too bad. Definitely refer back to your inference rules if you're having trouble with any of the cases. Otherwise, let's plan on office hours tomorrow after class, and I'll hang out for probably about 45 minutes, an hour for that session. And if we need more, we can probably schedule some stuff. Let's see what else. We'll have an optional midterm out on Friday. That'll basically cover all of the PL topics that we've gone over since the last midterm. There might be some questions on there that were on the first midterm, not sure yet. But stay tuned for that. I should hopefully be writing it tomorrow. It'll be pretty similar to the last one, mix of old and new questions. And let's see. Lecture notes for this week are on Canvas. So the lecture notes I'm lecturing off of the next couple days, probably today and tomorrow, come from really awesome guy. His name's Frank Fenning. He's probably one of the most prolific writers in the kind of functional programming and programming languages space. Don't know what institution he's at right now, but he's, let's see, what does it say? It doesn't say on the lecture notes. Or he's at CMU, so Carnegie Mellon, really big PL guy. He also is just a very good writer. So the notes are actually fairly approachable. If you do want to kind of go back over those, there are 206 pages of notes. I think it's for a full semester class. We're only going to cover probably the first 10 pages or so, maybe a touch more than that, but just to give us an idea of how the Lambda calculus works, and some more about kind of foundational computational models. So it's kind of probably the most theoretical will be the whole class, but it's some neat stuff. It's good to know, and it can be very handy later on. So let's see. Lecture notes available on Canvas. Okay, and then the next few weeks. I was a dummy. Last week, I think I said we had 3 weeks. It's from today. We have 3 weeks left of class. So that means I'll probably pull out my parsing lectures, and we'll probably cover parsing in full and combinators. It's a really good topic. It's a little bit more on the functional programming side of things, but it does kind of tie everything together, and it'll let us write our programs in concrete syntax and then parse those out and run them. So it kind of puts a nice bow on everything that we've talked about. We'll probably start that next week. We'll do a couple kind of miscellaneous topics this week. So Lambda calculus probably today and tomorrow. And then I'll pull out a good, 1 hour lecture on Thursday of something else, kind of miscellaneous. Not sure on that yet. So if you guys have any ideas or something that you for sure want covered from this list right here, definitely say something. Can definitely tailor the last few weeks. We've covered like the really, really important stuff. And now it's just kind of pulling stuff we want to go over. We'll definitely cover parsing. But other than that, definitely kind of happy to steer the class towards your guys' interests. Stuff I really like to go over are domain-specific languages, which we'll do a little bit with parsing. And then I guess all the bullet points are good things to go over. And the more powerful type systems are really cool and starting to gain some traction in industry. So it might be something useful to maybe touch on a little bit just to give you a little taste of it. I think that's it as far as logistics go. I think there's some questions in chat. Oh yeah, so if you do want to take midterm 2, It will be basically it's optional in the sense that if you don't take it, it won't count against you. If you take it, it's counted like a normal grade. So it's just whether or not you take it is up to you. Obviously, with it being graded like that, it could hurt you. So keep that in mind. That being said, because a lot of the questions are going to be repeat, it might be in your interest to take it. That being said, if you got 100% on the first midterm, probably don't need to take it. It's completely up to you. It's mostly so you guys can pad your grade if you'd like. I didn't want to make a second one mandatory because I think early on I said we'd only have one. So we'll stick to that. But if you do want that, you will have it. So Joseph says about financial, and they were saying to me that it's all functional programming and Lambda functions. If that's the case, into on Lambdas. So yeah, so Joseph is interested in kind of the financial sector and financial algorithms. And yeah, so we can definitely do a bit of a deeper dive on kind of functional programming and Lambdas. The big thing actually probably that would fit that are going to be these kind of monads, applicatives, monoids, and functors. So those are algebraic abstractions that are really common in functional programs. And I know the financial sector uses those a ton. So that could be a useful lecture for you. So yeah, I'll keep that in mind for sure. I really like lecturing on that stuff too. It's really neat, really powerful programming abstractions too. So, but yeah, if anyone else has any thoughts, we can maybe make a Piazza post about it. I think I caught up also on a side note on Piazza earlier today. If I did miss any questions, say something in chat and I'll take another look. I think I hit all the ones that hadn't gotten answered or weren't, or were still relevant for one reason or another. So if I missed one, they'll let me know. Otherwise, let's kind of jump into today's material if there aren't any more questions. So today we're going to start just kind of with a little bit of a historical note. This might be important for your quiz today, one question. So back in the 1930s, 40s, there are these three big names as Kurt Gödel, Alonzo Church, and Alan Turing. You guys have almost certainly heard of this guy. He's kind of the father of modern computer science, is how he's often referred to. Alonzo Church was his doctoral advisor. So they're kind of very entwined. You guys have probably heard of the Church-Turing thesis. That was named after Alonzo Church and Alan Turing. I'm sure you knew the Turing part, but most people don't know about Alonzo unless you're kind of in the field. So they had a good relationship with each other. And then there's this Kurt Gödel guy. These guys all about the same time, I think it was within a few years of each other, discovered different foundational models for computer science. And we still use two of them today. The most famous of these is Alan Turing's Turing machine. And this is typically a little kind of input-output machine that reads in a tape that has some symbols on it. And those symbols are able to kind of shift the tape around, write and erase things on and off of the tape, and do computations that way. It's fairly complicated to go really deep into it right now. We don't usually program with these, but it is a foundational model. The kind of thought is you can program anything with one of these machines. Alonzo Church had another system that was equivalent to the Turing machine. This is called the Lambda calculus. This is what we'll spend most of the day talking about. And then Kurt Gödel had another equivalent kind of formulation of what computation is called general recursive functions. And then some other just kind of historical notes. If you guys haven't seen the movie, now I'm drawing a blank on the name of the movie. Imitation Game, is that what it is? That sounds right. Correct me if I'm wrong. There's a movie called Imitation Game about Alan Turing and his work on decoding the Enigma machine in World War II. Really cool movie if you haven't seen it. Alonzo Church, put a note, he's Turing's advisor on his, I believe it was on his doctoral thesis. And then Kurt Gödel is actually most well known for kind of breaking mathematics. Definitely worth looking into this guy if you're interested. He caused a big fuss when he proved that basically mathematics is incomplete, and that applies to computer systems as well. And what incomplete means is kind of a formal thing, but it's very interesting. It caused a big ruckus in the formal math community back in the 20s, 30s. Really pissed off a guy named David Hilbert, another really big deal in mathematics. Really good book called Gödel, Escher, Bach about him. If you guys have not heard of this book. The Eternal Golden Braid. And if you read this book, it will make you for sure a better programmer, better computer scientist. It's really an awesome book. It's long, but don't let that scare you. I read it, I think shortly after I graduated with my CS degree. And it has changed how I think about computer science more than any other thing I've read probably. And just good for kind of getting kind of general computer science thinking baked into you. So definitely would recommend that. It's by a guy named Douglas Hofstadter. Just an awesome book. So a bunch of historical notes there. Today we're going to primarily be studying Alonzo Church's Lambda calculus. So we've already introduced kind of lambdas before for the sake of anonymous functions in our programming. But today we're going to kind of see why do we use this lambda notation? Where does it come from? So we'll talk about the lambda calculus. Our lead-in, a couple examples. So normally in mathematics, we like to talk about functions, things that look like this: f of x equals, say, x plus 5, or something like g of y equals, say, 2y plus 7. These are the things we typically deal with in, like, say, a math class. We might ask, how do you differentiate this? How do you integrate it? What happens if you apply f to g? Does that do something? What if I give f and x? That gives me a value out. But we never really talk about what f and g are in a formal sense. We just kind of know that when we give it an x or a y, we're supposed to substitute. And that's kind of where we leave it in math. We don't ever really dive into what these function things are in a formal sense. And it was Church that kind of laid some of this groundwork. What is a function? What if we treated functions like they were a mathematical entity? Because up here, it's kind of using functions as, as a means to an end, versus treating them as first-class mathematical entities. So I'll write that down. Church treated functions as first-class entities in mathematics. Can anyone parse what first class means here? What do I mean by first class? So pseudo says it doesn't depend on any other entities. I like it. It's okay. It doesn't quite capture everything. Any other thoughts? Anyone else have any thoughts on what first class means? So I'll write down Pseudo's answer. It doesn't depend on other entities. I could nitpick this one. I don't love it, but it's a good kind of gives you a gist of the idea. The kind of definition I'd prefer is that if something's first class, it supports operations that other entities in the language support. Sorry for the bad handwriting today. I don't know what's going on. Maybe too much coffee. So for instance, when we talk about, say, a first class function, that means we can pass functions to functions and treat them and, and say like x equals a function, right? So in this sense, this was the first time where we said, f is equal to a function, not like f of x is equal to something else, right? So this is a subtle difference from how we're going to start writing these function things. And instead, we're going to write these as lambda abstractions. So f of x is x plus 5 will instead be f equals lambda x dot x plus 5. And then our other example, g of y is equal to 2y plus 7 is instead written g is equal to lambda y 2y plus 7. Now, this doesn't seem like some interesting change, and in some sense it's not, but it does kind of tell us what we have here. Instead, before with this on this side, we couldn't talk about f on its own. Whereas here, f and g are kind of defined as their own objects. They're their own thing. They're not, f with respect to x, right? You don't need to give it an x. I can pass this function around on its own. So while it's a subtle notational difference, it does allow us to start treating these in a different way. And then we start talking about, okay, well, how do we plug stuff in? So I could write something like, I can still write, g of 5, for instance, and then that equal 2 times 5 plus 7, so 17. I could also say, maybe I didn't give g a name, and I had g of y dot 2y plus 7. And then I applied this to 5. I could have that all inlined like that as well. That'd be 17. So there's a couple different ways we can write these things now, right? And we don't necessarily need to give every function a name, whereas before, with this notation, we did. Here we can actually have an anonymous function with the lambdas. So that's something powerful we do get here. Any questions so far? Getting caught up with my notes real quick. I don't see anything yet, so please do stop me. It'll get confusing here in a minute. So let's talk about what it takes. Let's talk about this as kind of formally, right? Can we give some syntax for this? Kind of in the style we're used to, like as expressions. Do we think we could write that as a set of expressions? We certainly could. So Note this is a different expr than we've talked about in the last few weeks. I could call this, say, maybe I have construct for lambda. Lambda takes maybe a string for the variables, and then an expression for the body. We'll also have application. Or I'll just say app. App takes two expressions and applies them to each other. And then lastly, we have variables. Variables just take a string, and that's applying the variable, calling up the variable for use, right? We write these, make this a little smaller and give you the concrete syntax. So as concrete syntax, we might write something like lambda x dot e. Here we might write e1, e2. And then a variable is just going to be something like x, right? Bear with me for a quick second. All righty. So these are the only constructs we need for the lambda calculus. And I want to note, this is universal. What do I mean by that? Can represent any computation. All right, sorry, give me a second, scroll down in my notes. Let's talk about a few functions that we can write right now without anything else. So right now we don't have any data, right? So we haven't defined anything like true or false. We also don't have the numbers, anything else. We just have functions. And we'll come back to this little fact in a second, because it turns out we can represent numbers, we can represent Booleans, anything we would want with these constructs. And this is all we need. We just need functions, application, and variables. So we'll come back to that in a minute. But first, let's talk about a few functions we can write. Or actually, maybe I'll leave that as a question. What functions do we think we can write for sure with just this notation, without anything else, any tricks that I haven't introduced yet? Anyone have an idea of like a really simple function we could write? Yeah, so like the identity function, for sure can do that one. So let's do that. Could do the identity. And how do we write the identity? Can somebody write it in chat for me? Kind of using this notation. I'll give you guys a minute or two to try that out. How would you write the identity function as a lambda? I think we did talk about this a few weeks ago, maybe. Anyone taking a stab at it? Let's get involved. Come on, do some typing for me. Awesome. Conlin's got an idea. So lambda x, and then the variable x, so something like that. And that's it. That's the identity function. Now, how do we know it's the identity function? Let's try applying it. So when I give a name like this, there's a pretty simple way to execute it. So if I did something like ID on, say, ID on, let's throw a number in there. I told you earlier we don't have numbers yet, but pretend we do for a second. We can evaluate this by first substituting ID for what it's defined as. This is one of the other strengths of the lambda calculus. So instead of ID, we can write lambda x dot x and substitute that in for the name ID. We have that applied to 10. Okay, well, how does 10 get substituted in there? So we have some new notation for that as well. And we'll write x with x substituted in, or wait, that's the wrong way. Wrong order, I think. It would be 10 substituted in for x. And then because we just have the x, we get 10. So that's the identity function. Make a note on the notation here. Means substitute E in for X. Does that make sense to everybody? Any questions so far? Yeah, so we kind of verified the identity function works how we expect it to. What's another function we can write with just these constructs? So just the lambda, variables, and application. No other tricks. Might be kind of hard to come up with this one. So I'll give it to you. We also have function composition. This is another really simple function that you guys could write with just these constructs. Now that I've kind of given it to you, does anyone have an idea about how you might write this? Function composition. So in the past, we might have written function composition kind of in the old style, like this. We might write f dot g of x is equal to f of g of x. How can we write this in our new style? I'll give you guys this quick second to take a try at that. Okay, we got some answers coming in. I like it. Lebesgue just went straight to kind of the best form of this. So we could start by writing f dot g and then writing lambda x of f of g of x. But this isn't quite right because we still have that f and g on the other side. And we don't want these over here. Because these are still variables, right? So can we get those on the right-hand side of the equal sign? And that's exactly what Lebesgue has just done. So instead we could write composition equals lambda f. I'm changing the variable names a little bit from what he put. Lambda g, lambda x is f of g of x, like so. Any questions about why we wrote that like that or the ordering? Does anyone remember what this is called when we use multiple lambdas to get multiple arguments into our function? We talked about this earlier in the semester, quite a bit. What do we call that? Not quite higher, not higher order. Yeah, Ronak's got it. It's called currying. Right on. Yeah, so this is kind of where currying comes from originally. And it started with the lambda calculus. So if I need more variables, I just introduce more lambdas, as simple as that. Don't need any notion of products or pairs, nothing like that. No tuples are necessary. I just need more lambdas. Now, why is that? It's because when I go and apply stuff to this, it'll apply from the outside in. So I can start by giving it an F. Then I give it a G and then an X, and it'll substitute as we go. It's that handy little substitution we did before, just like you're used to with functions in math. So it's not really any different. So those are the two big functions we're used to so far. I'm not going to talk about, at least yet, I think tomorrow we'll introduce this. There are basically three semantic rules for the lambda calculus. I've kind of given you the syntax so far and some examples. Put a note here. It only takes, yeah, 3 to 4 rules. It kind of depends how you nitpick if one of the rules is part of the other rule or not. So 3 or 4 rules define the lambda calculus. We'll talk about these tomorrow. I just wanted to kind of make a note of that, especially if you're kind of reading through the notes overnight. You'll come across section 4 and 5, where they'll talk a little bit about these rules. We'll introduce them tomorrow, though, because it's a little bit more nuanced. Today, I just want to introduce you guys to using the calculus. So I mentioned before, we don't have any data. Get a new page for this. So I'm going to pose a question to you guys. If the lambda calculus is universal, how must we represent data like true and false. I'll let you guys stew on that for a second. If you have ideas, throw it in chat. Because this is a really kind of important thought. And I'll give you a little bit of a hint. We definitely can represent these, and we must, right? True and false have to be able to be represented if this is going to be universal. How do we represent that? So pseudo says, yeah, I won't write your name down. 0 and 1. Problem with using 0 and 1, though, is that we don't have numbers. I used them up above for example's sake, but we actually don't. All we have is application, variables, and lambda abstraction, or functions, right? Lambda abstractions are functions. But it's a good thought. It's not wrong per se. I mean, if we had 1 and 0, we definitely could represent true and false with 1 and 0. But that would require us to have 1 and 0 first. How could we represent true and false? Maybe I'll refine the question a little bit. Don't necessarily give me the exact definition of true and false, for instance, but how must we, what do we have to use? I think that's maybe the better question. If we only have 3 constructs, one's a variable, one is application, and the other's abstraction, what kind of makes the most sense to use for data? Kind of a hard question to answer. Does anyone think they have an idea? If not, I'm going to give it to you. This kind of goes without saying. We have to use lambda abstraction. And why is that? Well, application makes the computations happen, right? So application kind of plugs stuff into functions. Variables on their own don't really do anything. So that's not really the right way to represent data. So instead, we need to use lambda abstraction. It's kind of the most stable thing in some respect. This will kind of make a little bit of sense once we start defining these. So let's talk about encoding true and false. This will probably be the most confusing thing we talk about all semester, is this encoding right here. But I think if you take a little bit of time to try and understand what's going on, it makes a lot of sense. So I'll give you the definitions, and I'll let you guys kind of just spend a minute or two with them. And see if you can get an intuition and try and explain it to the rest of the class for us. So true is equal to lambda x, lambda y, x false is equal to lambda x, lambda y, y. Why do we define true and false like this? Ooh, pseudo came quick with it. It makes sense. It's like a switch. Very quick answer. Does anyone else have, I really like that. It's kind of like a switch. Does anyone else have any other intuitions? I'll give you a couple of minutes because there's a bunch of different ways to look at this. It's, you know, what happens if you plug something into it, right? If true and false are functions, it means you can plug stuff in. What happens if you do that? Conlon says it's kind of like case matching with an if then else statement, right? But it's where it's kind of almost already applied out. So it's not quite like if then else. Actually, not at all, right? Because if then else, you have some notion of you don't know if it's true or false yet. But this does the practical part of it, right? It does the result. I'm going to paraphrase you a little bit, Common. Yeah, really good observation there. Arthur says it's because it gives us exactly two options and it can only be one or the other. In any scenario like that, true or false is representable, right? So if we think about this, and I actually really like that. I hadn't really thought about that, Arthur, in that way. That's awesome. If you think about what a function on two arguments does, if I don't know what x and y are, I have a two-way choice. And I can choose x or y. With true, I pick x. With false, I pick y. And that gives us two different possibilities and only two, right? So I really, really like that. I'll paraphrase you as well, Arthur, because that's a longer one. A lot of good discussion here. Pseudo, so you can put the desired true output in the X and the false output in the Y. The desired true output. Yeah, so you could think about this as like being almost an applied if then else in that respect. So this is maybe going to what Conlon was saying is if I don't know if it's true or false, right? I know I have a Boolean maybe, and I have a true value and a false value. I'll pass both of those in there and then let the function tell me if it's true or false by giving me an output, right? So in that respect, it's like true or false. It's like lambda x is looking for an x and you're feeding it one, so it's satisfied. When you give it a y, it's not satisfied. Joseph, I don't think so. Without some elaboration, I'm not sure if that makes sense. But type some explanation. We'll see if there's something to that. You might be on something there. Then pseudo says, so essentially it's like condition if true, if false, right? So it's kind of like you're writing an if true, if false function. It's exactly like that. Yeah, it's like if you wrote two separate functions that were just did something if it's true, otherwise it does nothing, or did something if it's false, otherwise it's nothing, right? It's kind of inverting an if then else statement, right? In some respect. I like it. Really good discussion here, guys. Yeah, so that's the intuition. That's awesome, guys. If you think about what true and false do, kind of typically, you would never just, unless you're outputting true and false, say to the screen, if you ever used a true and false in the program, you're only ever going to branch in one or two ways, right? They're used to branch or pick between two possible executions of the program. Right? And that's essentially what these two functions do. So if we think about it as choosing between two different possibilities, we don't know if, say, we have a true or false, but the true or false know how to handle the branching in our program. If we think X is another function and Y is another function, and we ran one, it would say run X, run Y, if it's false, right? Here's a function based on, here's the X, so think of it, so it's just false. Joseph, I am not sure if that is the right way to think about it. Let's play with them a little bit, and I think it'll clear it up. Yeah, I'm not sure. Without doing some more prodding, I'm not sure where you're going with that still. And that's okay. Yeah, it is kind of a weird thing. You do have to kind of make some guesses while we're trying to understand this. So thanks for trying. That's awesome. So how do we write a function on Booleans, right? So here's our question. Can we write, say, the not function? Okay, we have true and false, but we don't have pattern matching, right? So can I write the function, and I'm going to write it in the other style, right? Where we kind of define this piecewise, where not true equals false, not false equals true. Can we write this as a lambda? Okay, I'll give you guys a minute to try that out. And your big hint, and this is a big hint, remember true and false are functions. And see if you can write that. I'll give you a minute, mostly because I need to use the restroom. So. All righty. Let's catch up. I'm catching up with the chat. So Arthur says, and take the previous lambda and reverse it. So lambda x dot y, lambda y dot x. So that doesn't quite work because I think there you're trying to do pattern matching. And remember, x and y are just variable names. So you could easily just swap them. So you've just written kind of the identity function twice. I'll give you a hint. You need to use the true and false function somewhere in this definition. So remember, we could start out by writing this, and I'll give you kind of the first little bit. As say lambda, we'll use b dot, and then what could go here? We could say like not, I guess not equals to kind of be consistent. Give it a name. Any ideas? So B's our input. B is going to be either true or false, though, right? We have some options here. We could either add more lambdas, or we could try applying B to something. What happens if we try and apply B to something? So B then expects two arguments, right? Because B is either true or false. Okay, we'll add that stipulation here. And I'll pull our definitions of true or false back up because you guys might want those. Ooh, I like this. So Arthur's got an idea. Let's try this out. Arthur says not should equal lambda b dot b on false and true. Okay. Lebesque says, ooh, this is interesting. Not, did he sub in? Oh, Lebesque says the same thing, it looks like, just spelled out. Okay, cool. And we'll actually write it in the sub form in a second. So perfect. This is it. Why does this work? This doesn't make a lot of sense initially. So let's try applying this. What happens if I do, for instance, not, that's not the right color. I used brown for examples. Not true. Okay, so I can start subbing stuff in. Let's substitute in not and also substitute in the true part, okay? So not, as we've defined it, is lambda b dot b false true. Okay, put big parentheses around there. And then we've given it true. True is lambda x dot lambda y dot x. Okay, now we have an application. I need to plug in this for b. What does that do? Okay, so if I plug that in for b, I get B, false, true. I'm going to go through all the steps here. With, okay, now we're using square brackets, lambda x, lambda y dot x subbed in for B, which is lambda x, lambda y dot x on false and true. You guys see where I'm going? Now we have another application. So we get false applied to this. So I have lambda y dot x with false substituted in for x. And we still have true out there. This then becomes lambda y dot true applied to true. And then if we substitute true in for y, there's no y's, and we end up getting true. Wait a second, that's not right. We get false. Sorry, I subbed the wrong thing in there. We get false here. This is why you don't skip steps. And then you finally get false, not true. Okay, so good work to those that got that. That's a tricky problem. So Arthur's catching on to this pretty fast. This is tricky. If you don't quite understand this all at first bat, keep playing with it. You know, keep working through it and do these applications, and it'll start to become more clear. Definitely a tricky problem to do, though. Let's see. I'm worried that if we try and do another exercise, we will run out of time. Those problems take a little while to do. Yeah, I think we'll break there for the day. Tomorrow we'll do, I'm thinking, do a couple more examples on the Booleans. We'll define the numbers and show you how you can write functions on numbers, which will be a fun exercise, because those, if you thought Booleans are hard to grasp, the numbers are pretty wild too. We call those church numerals. And then we'll talk about some of the formalities. You know, where do these semantics come from? They're basically those 4 rules I was mentioning before. We'll define those, give those kind of some formal meaning tomorrow. So that's the game plan. We could easily probably stretch this into 3 days, so we might just do this all week. We'll keep playing with it though. So if you didn't understand kind of what happened there at the end, keep kind of play around with it a little bit tonight. Try and get a grasp for it. And we'll pick back up there and try and write conjunction or and tomorrow. So otherwise, have a good one, everybody, and I'll see you tomorrow at 5.